Welcome friends to my channel. Today I will be discussing the subject strength of materials MCQ question from Khurmian Bukta book. Question number 251 to question number 300. So let's start. Question number 251. The maximum deflection of a cantilever beam of length L with a point load W at the free end is for the cantilever beam as shown AB. If the point load is acting at the free end, the maximum deflection at B will be Ymax equal to WL cube by 3EI. So option number A is the correct answer for this question. Next question 252. The maximum deflection of a cantilever beam of length L with a uniformly distributed load of W per unit length is for the cantilever beam subjected to uniformly distributed load W per unit length, the maximum deflection at the end B will be Ymax equal to WL cube by 8EI. So option number B is the correct answer for this question 252. Next question 253. In a cantilever beam of length L subjected to uniformly distributed load W per unit length, the maximum deflection lies at the fixed end. No, the maximum deflection will be at the free end. Option A is the right answer, but for this question option B is the right answer. Next question 254. Two cantilever beams A and B are shown in the figure 2.46. The ratio of maximum deflection of the beam A to the beam B is. The beam A is, as per the question, cantilever beam subject to uniformly distributed load W per unit length. So the maximum deflection Ymax will be WL to the power 4 by 8EI. And question for the beam B, as per the question, the cantilever beam subjected to uniformly distributed load with its half of this span subjected to uniformly distributed load. So for this beam subjected to this kind of load UDL up to the half of this span, the maximum deflection Ymax will be 7WL to the power 4 by 384 EI. So friends, if we make the ratio Ymax for the beam A divided by Ymax for the beam B, we will get the value 48 by 7. So for question number 254, option D is the right answer. Next question 255. Two cantilever beams A and B shown in the figure. The ratio of maximum deflection of the beam A to the beam B is, as per the question, for the beam A, the cantilever beam subjected to point load at the free end, the maximum deflection will be WLQ divided by 3EI. And as per the question, for the beam B, the cantilever beam subjected to uniformly distributed load and its total load will be W. So maximum deflection Ymax will be WLQ divided by 8EI. So if we make the ratio Ymax or deflection for the beam A divided by deflection for the beam B, Ymax B, which will be equal to 8 by 3. Option number B is the right answer for this question. Next question 256. A cantilever beam of length L carries a gradually varying load from 0 at the free end and W per unit length at the fixed end. The maximum deflection lies at. We know the maximum deflection of a cantilever beam will be at the free end. So option A is the right answer. Next question 257. The value of maximum deflection of a beam given in the question 256 is if the cantilever beam subjected to uniformly varying load from 0 at this free end and maximum to this fixed end, the maximum deflection Y will be WL to the power 4 by 30 EI. So option number C is the right answer for this question. Next question 258. The maximum deflection of a fixed beam carrying a central point load lies at the. Option B is the right answer, center of the beam. Next question, the maximum deflection of a fixed beam of length L carrying a central point load W is. Option C is the right answer, WL cube divided by 192 EI. As per the question, the fixed beam subjected to a central point load W, the maximum deflection will be WL cube by 192 EI. So for question number 259, option C is the right answer. Next question 260. The maximum deflection of a fixed beam of length L carrying a total load W uniformly distributed over the whole length is. As per the question, a fixed beam subjected to uniformly distributed load W per unit length, the maximum deflection of the beam will be at the center and it will be equal to WLQ divided by 384 EI. So for this question, option D is the right answer. Next question 261. Two fixed beam A and B are shown in the figure 2.48. The ratio of maximum deflection of the beam A to the maximum deflection of the beam B is. As per the question, for the beam A, which is fixed beam subject to uniformly distributed load and the total load is W, the maximum deflection will be WLQ by 384 EI, which is represented by Y max A. And for the beam B, as per the question, which is fixed beam subjected to point load W at the central point of the beam. So Y max or deflection will be, which is represented by Y max B, will be equal to WLQ divided by 192 EI. So if we make the ratio Y max A divided by Y max B, we will get the value equal to 1/2. So option A is the correct answer for this question. Next question 262. The product of Young modulus and moment of inertia is known as. Option number C is the right answer, flexural rigidity. Next question 263. A simple supported beam A of length L, breadth B and depth D carries a central load W. Another beam B of the same dimension carries a central load equal to 2W. The deflection of the beam B will be how much as that of the beam A? So let's see. As per the question, for the beam A, which is a simply supported beam subject to a central point load W, and as per the question, for the beam which is also simply supported beam subjected to point load but the amount of load is 2W. So the question is asked here, the deflection of the beam B as compared to beam A. So we know deflection is proportional to load. So deflection of the beam B will be twice that the deflection of the beam A, as the load is double. For question number 263, option C is the right answer. Next question 264. A simply supported beam A of length L, breadth B and depth D carries a central point load W. Another beam B has the same length and depth but its breadth is doubled. The deflection of the beam B will be how much as compared to the beam A? In question number 264, beam A, the simply supported beam subjected to a central point load W, and for the beam B, which is simply supported beam subject to a central point load W. But for the beam B, the breadth is doubled, length and depth is constant for both the beam. So we know if the point load is acting for a simply supported beam at the midpoint, the deflection will be WLQ by 48 EI. And we know moment of inertia I will be equal to BDQ by 12. So if we put the value of I in this equation, deflection, so we can write deflection varies as 1/B or breadth of the section of the beam. So here we can say the deflection of the beam will be inversely proportional to the breadth of the beam section. So we can also write deflection del 1 divided by del 2, which will be equal to breadth 2 B2 divided by breadth 1. B2 is the breadth of the beam B and B1 is the breadth of the beam A. So if we say B1 is X, so B2 will be 2X, and if we calculate the deflection for the beam B or del 2 will be half into del 1. So for question number 264, option B is the right answer. The deflection of the beam B will be 1/2 as compared to the beam A. Next question 265. A simply supported beam A of length L, breadth B and depth D carries a central point load W. Another beam B has the same length and breadth but depth is doubled. The deflection of the beam B will be double as compared to the beam A. So let's find out it is right or wrong. For the question number 265. Both the simply supported beam is subjected to central point load W, but their length and breadth is same, but the depth of the section for the beam B is double. So what will be the deflection of the beam B as compared to the beam A? So we know deflection of the beam del will be equal to WL by divided by 48 EI. I is the moment of inertia of the section of the beam, so I will be equal to BD cube by 12. And if we put the value of I in this equation, so deflection del varies as 1/D cube. The deflection of the beam will be inversely proportional to the depth of the beam section. but the depth is cubical in relation. So if we make the ratio deflection for the beam A, which is del 1, and deflection for the beam B, which is del 2, del 1 by del 2, which will also be equal to depth d2 divided by d1 to the power whole cube. And if we say d1 or depth of the beam section for beam section A is x, so the depth of the beam section B will be 2x. And if we calculate the value, we will get del 1 equal to 8 into del 2. So the deflection of the beam A will be 8 times the deflection of the beam B. So for question number 265, option number B is the right answer. Next question 266. The two simply supported beam A, B of same breadth and depth carries a central load W as shown in the figure 2.49. The deflection of the beam B will be how much as that of the beam A. This is the beam A, simply supported beam subjected to central point load W, and this is the beam B, simply supported beam subjected to point load W, but the length is double. So we know the deflection of the simply supported beam for a point load at the center, deflection del will be equal to WL cube divided by 48 EI. So from this relation we can say del varies as L cube. So we can also write del 1 divided by del 2. Del 1 is the deflection of the beam A, and del 2 is the deflection of the beam B. So del 1 divided by del 2 will be equal to L1 by L2 to the power whole cube. And if we calculate, the value will be del 2 equal to 8 into del 1. So the deflection of the beam B will be, option D is the right answer, 8 times as that of the beam A. Next question 267. Two beams A and B carrying a central point load W are shown in the figure 2.50. The deflection of the beam A will be how much as compared to the beam B. For the beam A, the fixed beam subjected to a point load W, the maximum deflection del 1 max will be equal to WL cube divided by 192 EI. And for the beam B, which is simply supported beam subjected to a central point load W, the maximum deflection W2 del 2 max will be WL cube divided by 48 EI. So if we make the ratio del 1 max divided by del 2 max, the value will be 1 by 4. So we can also write del 1 max equal to 1/4 into del 2 max. So for question number 267, option number B is the right answer. Next question 268. Match the correct formula for deflection given in group B for the beam given in the group A. So friends, I have drawn the beam from that question 268. So first beam, the cantilever beam subjected to a point load W at the free end, the maximum deflection will be WL cube divided by 3 EI. Next beam, the cantilever beam subjected to a uniformly distributed load W, total load W, the maximum deflection will be WL cube divided by 8 EI. Next beam is C, simply supported beam subjected to a central point load W, the deflection will be WL cube by 48 EI. Next beam D, the simply supported beam subjected to a uniformly distributed load, and the total load is W, the maximum deflection will be 5 WL cube divided by 384 EI. For the next beam, fixed beam subjected to a central point load W, the maximum deflection will be equal to WL cube by 192 EI. For the next beam, which is fixed beam subjected to a uniformly distributed load, and the total load is W, the deflection will be equal to WL cube divided by 384 EI. Next question 269. The product of the tangential force acting on the shaft and its distance from the axis of the shaft is known as. Option number B is the right answer, twisting moment. Next question 270. When a shaft is subjected to a twisting moment, every cross section of the shaft will be under, option C is the correct answer, shear stress. Next question 271. The shear stress at the center of a circular shaft under the torsion is 0. So option number A is the correct answer. Next question 272. The shear stress at the outermost fiber of a circular shaft under the torsion is, option C is the right answer. 273. The torsional rigidity of a shaft is given by torsional rigidity, which is T by theta. Option number B is the right answer. Next question 274. When a shaft is subjected to torsion, the shear stress induced in the shaft varies from option number C is the right answer, 0 at the center and maximum at the circumference. Next question 275. The torsional rigidity of a shaft is expressed by the torque required to produce a twist of 1 radian per unit length of a shaft. Option A is the right answer, true. Next question 276. For a shaft, the shear stress at a point is, option B is the right answer, directly proportional to the distance from the axis of the shaft. Next question 277. The polar moment of inertia of a solid circular shaft of diameter d is, option C is the right answer, pi d to the power 4 divided by 32. Next question 278. The polar moment of inertia of a hollow shaft of outer diameter d and inner diameter small d is, option C is the right answer, pi by 32 within bracket d to the power 4 minus small d to the power 4. Next question 279. Which of the following is correct torsional equation? Option number B is the right answer, T by J equal to tau by R equal to C theta by L. T is the torsion, J is the polar moment of inertia of the shaft section, tau is the shear stress, R is the radius of the shaft, and C is the modulus of rigidity of the material of the shaft, and theta is the angle of twist, L is the length of the shaft. Next question 280. The torque transmitted by a solid shaft of diameter d is, option B is the right answer, pi by 16 into tau into d cube. Tau is the maximum allowable shear stress. Next question 281. Two solid shaft A and B are made of the same material. The shaft A is of 50 mm diameter and shaft B is of 100 mm diameter. The strength of shaft B is how much as compared to the shaft A? As the two shafts are made of same material, so their strength is directly proportional to their polar modulus. Polar modulus Zp is equal to pi by 16 into d cube, and we can write Zp varies as d cube. So we can also write Zp for the shaft A and divided by Zp for the shaft B, which is also equal to d1 divided by d2 to the whole cube. And if we calculate the value, Zpb will be equal to 8 into Zpa. For question number 281, option number D is the correct answer. The strength of the shaft B is 8 times as that of the shaft A. Next question 282. In the torsion equation, T by J equal to tau by R equal to C theta by L. The term J by R is called polar modulus. Option C is the right answer. Next question 283. The polar modulus for a solid shaft of the diameter D is, option B is the right answer, pi d cube divided by 16. Next question 284. The polar modulus for a hollow shaft of outer diameter d and inner diameter small d is, option C is the right answer, pi by 16 into capital D to the power 4 minus small d to the power 4 divided by capital D. Next question 285. The torque transmitted by a hollow shaft of outer diameter capital D and inner diameter small d is, option number C is the right answer, pi by 16 into tau into within bracket capital D to the power 4 minus small d to the power 4 by capital D. Next question 286. A shaft revolving at omega radian per second transmits torque T in Newton meter. The power developed is, option number A is the right answer, T into omega watts. Next question 287. Two shafts A and B transmits the same power. The speed of shaft A is 250 rpm and the speed of the shaft B is 300 rpm. The shaft B has the greater diameter. We have to calculate and determine the option. We know power P will be equal to 2 pi nt divided by 60. N is the revolution of the shaft per minute and T is the torsion of the shaft. So power P1 for the shaft A will be equal to 2 pi into the revolution per minute. N for the shaft A will be 250. So power P1 will be equal to, we know the NA will be 250 rpm and NB is the 300 rpm, and D1 is the diameter of the shaft A and D2 is the diameter of the shaft B, and T is the transmitted torque. So the power P1 for the shaft A will be equal to 2 pi into 250 into pi d1 cube into shear stress tau divided by 60 into 16, and the power P2 for the shaft B will be equal to 2 pi into 300 into pi d2 cube by 16 into tau divided by 60. So we know the equation 1 will be equal to equation 2 because the power is same for both the shafts. So if we equate the equation 1 and equation 2, we will get d1 divided by d2 will be equal to 1.2 to the power 1/3. So for question number 287, option B is the right answer, false. Next question 288. Two shafts A and B have the same material. The shaft A is solid of diameter 100 mm and the shaft B is hollow with outer diameter 100 mm and inner diameter 50 mm. The torque transmitted by the shaft B is how much as that of the shaft A? So torque for the shaft A, TA will be pi by 16 into shear stress tau into d cube, which is 100 mm, 100 cube. Torque for the shaft B, TB will be equal to pi by 16 into shear stress tau into within bracket the outer diameter 100 to the power 4 minus inner diameter 50 to the power 4 divided by the outer diameter, which is 100. So if we make the ratio TA divided by TB, we will get the value 16 by 15, and the torque TB will be equal to 15 by 16 into TA. So for question number 288, option number D is the right answer. Next question 289. The strength of the shaft is judged by the torque transmitted by the shaft. Option A is the right answer. Yes. Next question 290. Two shafts A and B are made of same material. The shaft A is solid and has a diameter capital D. The shaft B is hollow with outer diameter capital D and inner diameter D by capital D by 2. The strength of the hollow shaft is how much as that of the solid shaft? For the shaft A, TA will be equal to pi by 16 into shear stress tau into capital D cube, and torque for the shaft B will be equal to pi by 16 into shear stress tau into within bracket d to the power capital D to the power 4 minus d by 2 to the power 4, and d by 2 is the inner diameter of the hollow shaft divided by capital D. And if we calculate, the TB will be equal to pi by 16 into shear stress into 15 d cube divided by 16. So if we make the ratio TA by TB, we will get the value 16 by 15, and TB will be equal to 15 by 16 into TA. For question number 290, option number D is the right answer. Next question 291. Two shafts A and B are made of same material. The shaft A is of diameter capital D and shaft B is of diameter capital D by 2. The strength of the shaft B is how much as that of the shaft A? So we know the strength of the shaft is directly proportional to the polar modulus of the shaft. The polar modulus varies as capital D cube of the shaft. Capital D is the diameter of the shaft. So for the shaft A, the polar modulus ZPA divided by polar modulus for the shaft B ZPB, and if we make the ratio ZPA divided by ZPB, which will also be equal to capital D divided by capital D by 2 to the power whole cube, and if we calculate, we will get the value ZPB, or the polar modulus for the shaft B will be equal to 1 by 8 into ZPA. So for question number 291, option number A is the right answer. The strength of the shaft B is 1/8 of the shaft A. Next question 292. When two shafts of same length, one of which is hollow, transmit equal torques and have equal maximum shear stress, then they should have equal. Option B is the right answer, polar modulus. Next question 293. A circular shaft fixed at A has diameter capital D for half of its length and diameter capital D by 2 over the other half, as shown in the figure 2.51. If the rotation of the B relative to A is 0.1 radian, the rotation of C relative to B will be. So the figure is drawn here. From torsional equation, T by J equal to C theta by L equal to J by R, we can write theta is inversely proportional to 1 by J, and J is the polar modulus of the shaft and theta is the rotation of the shaft or angle of twist. So from this figure, the rotation theta 1 divided by theta 2 will be equal to Z2 divided by Z1, and Z will be equal to pi d to the power 4 divided by 32. So Z is proportional to d to the power 4. For the shaft ABC, the portion BC has different polar modulus and the portion AB has different polar modulus because their diameter is different. Diameters of this portion AB of the shaft is capital D1 equal to capital D, and the diameter of this portion BC will be capital D by 2. So we can write theta 1 by theta 2 equal to J2 by J1, which will also be equal to the diameter D2 divided by D1. If we put the value of D1 and D2, we will get d theta 1 by theta 2 equal to d by 2 divided by capital D to the power 4, and we know theta 1 is the rotation of the B relative to A, and theta 1 is 0.1 radian. If we put the value of theta 1 equal to 0.1 radian, so the value of theta 2 will be 1.6 radian. So for question number 293, option C is the right answer. Next question 294. For the two shafts connected in parallel and subjected to twisting moment, the angle of twist of each shaft will be same. Option number A is the right answer, yes. Next question 295. The strain energy stored in a solid circular shaft subjected to shear stress tau is. Option number D is the right answer, tau square divided by 4c into volume of the shaft. C is the modulus of rigidity of the shaft material. Next question 296. The strain energy stored in a hollow circular shaft of outer diameter capital D and inner diameter small d subjected to shear stress is. Option number D is the right answer, tau square by 4c into within bracket capital D square plus small d square divided by capital D into volume of the shaft. Next question 297. When a shaft of diameter capital D is subjected to a twisting moment capital D, the bending moment capital M, then equivalent bending moment ME is given by. Option C is the right answer, half into within bracket M plus root over of M square plus T square. Next question 298. When a shaft of diameter capital D is subjected to a twisting moment capital T and bending moment M, then equivalent twisting moment TE is given by. Option number A is the right answer, root over of M square plus T square. Next question 299. When a shaft of diameter D is subjected to a twisting moment T and bending moment M, then maximum normal stress is given by. Option C is the right answer, 16 by pi d cube within bracket M plus root over of M square plus T square. Next question 300. When a shaft of diameter D is subjected to a twisting moment capital T and bending moment M, then maximum shear stress is given by. Option C is the right answer, 16 by pi d cube within bracket root over of M square plus T square. So friends, I will be back in the next video. Please keep supporting me, and if you have any doubt about this solution, please let me know in the comment section as I said earlier. Thank you.